Welcome to the first lecture on the category of vector spaces titled Introduction, Groups and Fields. For my introduction, let me define the notion of vectors in the plane. Let R square be seen as usual as a Euclidean plane. Let O denote the origin. A translation of R square is a function tau from R square to R square, such that for any m in the plane, the quadrilateral O, tau of m is a parallelogram. The key observation is that if tau is a translation, then it is entirely determined by the image of the origin O. We can thus identify the translation tau with tau of O, or similarly with any pair of points m tau of m, as knowing one such pair entirely describes tau. If you give me any point in the plane, I can calculate its image by tau by drawing a parallelogram. Translations as functions can be composed. For two translation tau and tau prime, rewrite the composition of tau with tau prime as tau plus tau prime. I'll let you check that tau plus tau prime is again a translation. Translations can also be scaled. If lambda is a real number and tau is a translation, then lambda times tau is obtained as a unique translation which maps the origin to the point of coordinates lambda a, lambda b, where ab has a coordinate of tau of O. Together with these operations, translations are now what we call vectors. It is customary to represent vectors as arrows. As you can see on the pictures, we have two arrows, a black one and a green one. They represent the same translation, so they represent the same vector. Vectors in 2-dimension and 3-dimension are basic geometric objects which enable solving geometric problems using algebra. This is a very deep idea due to René Descartes, who introduced the notion of coordinates. Now, vectors can be in particular added together and scaled by a real number. The algebraic properties of these two operations form the foundations of the theory of vector spaces. Vectors are found in many applications. For instance, they are used in geometry, where vectors are akin to a translation. They are used in physics, where vectors model positions, velocities, forces, etc. They are used in computer graphics, where vectors are used to compute positions, normal to shapes, lighting, etc. Vectors are in fact found in many applications in engineering, mathematics, physics, chemistry, statistics, and others. Mathematics is about finding patterns which are at once common to many problems, yet rich enough to allow for interesting theorems to be deduced from them. In particular, a vector space is an algebraic structure which abstracts the properties of the vectors of the plane. Many spaces of functions have this same algebraic structure, with many applications from quantum physics to statistical analysis. Vector spaces themselves are built on top of other algebraic structures, namely Abelian groups and fields. We now introduce these structures and use them as a means to familiarize ourselves with the idea of an algebraic structure. Let's begin with groups. The properties of addition of vectors can be encapsulated in the following abstract structure. A group G star is a set G and a binary operation on G which satisfies the following three properties. Star is associative. There exists a neutral element for star, and every element of the group has an inverse for star. There are many examples of groups. 2D and 3D vectors with vector addition, of course, form groups. The set of n by n invertible matrices with matrix multiplication also form a group. So does R with addition, R with that 0 for the multiplication, the group of permutations or bijections of a fixed set for composition, and many more examples. In physics, for instance, groups are used to model symmetries. Now, we can prove many results for all of our examples of groups. Let's give an example. Here's a theorem. Let G be a group for all x, y, and z in G if x star y is equal to x star z, then y equals z. We are going to prove the theorem relying only on the assumption of the theorem and the three properties defining group. So let x, y, and z be elements of G such that x star y is equal to x star z. Now, by the property now highlighted in red of a group, there exists a x inverse in G so that x times x inverse is equal to x inverse star x is equal to E. Then we are going to prove our theorem with a string of equalities. First, using the now highlighted second property defining a group, there exists a neutral element E, so y equals E star y. Then, using the now highlighted third property, we replace E with x inverse star x. Using the first property, associativity of star, we can move the parenthesis to the right. The hypothesis of my theorem tells me that the element x star y can be replaced by the element x star z as they are equal. I then apply associativity once more to move the parenthesis back to the left. Apply the relation x inverse star x equal a neutral element E, and conclude, as E is neutral, that indeed y equals z by transitivity of the equality. This is the first theorem that we have proven in this lecture. We will actually use it quite often. And it is valid for any groups because I only relied on the general property of a group and, of course, the assumption of my theorem. Now, as a little notational detour, I want to record the following. If you look at what associativity tells you, in some ways associativity tells you how to apply the star operation to three elements. Star operation only applies to two elements at a time, but associativity tells you that if you have three elements, there is an identity between the two natural ways you could possibly apply the star operation to all three of them. This can be generalized to arbitrarily finitely many elements of G. There is a way to define x1 star x2 star x3 etc. star xn without writing any parenthesis because associativity ensures that this is not an ambiguous definition. We will use this notation all throughout our lectures. Now, let's return to proving interesting properties about groups. Groups enjoy many properties which are the subject of group theory. It is a vast, fascinating, beautiful field of mathematics. For our purpose, however, we only need a few simple, though very helpful, observations. Let's prove one more theorem. If G star is a group, and if E and F are both neutral elements for star, which means that if you compute x star E or F star X or any of those other products listed here, you always get simply back X for any element X of the group. Then F is equal to E. The proof is very short. Since E is neutral, F must be equal to F star E, because computing x star E for any X in the group simply equals X. So F equals F star E, but now F is also neutral. Therefore, F star E must be equal to E. So F equals E. Thus, we can talk about the neutral element of a group. It is unique. In the same vein, we can talk about the inverse of an element of a group. Indeed, suppose we have x, y, and z in a group with a property that, first of all, x star y equals y star x equal the neutral element E, so y acts as an inverse for x. And at the same time, x star z equals z star x equals E, so z also acts like an inverse for x. But then note that we have written in particular that x star y is equal to x star z, namely, they both are equal to E. And by the first theorem we have proven, we can conclude that y must be equal to z. So, neutral element is unique, and for each element of the group, its inverse is unique. The addition of vectors in geometry is also commutative, that is, the order in which you add the vectors does not matter. Yet commutativity does not follow from the properties of a general group. For instance, we showed that the set of n by n invertible matrices is a group for the multiplication of matrices. And certainly, as soon as n is at least 2, there are two invertible n by n matrices A and B, such that A times B is not equals to B times A. So, let's give a definition here. An abelian group is a group G plus such that for all x and y in G, x plus y is equal to y plus x. The addition, the operation on the group is actually commutative. Examples include the real numbers with addition, the real number without zero for the multiplication, etc. Now, here there are a couple of conventions that we will use throughout our lectures. Typically, though not always, but typically, the operation on an abelian group is denoted by plus, the neutral element of such an abelian group is denoted by 0, and the inverse of an arbitrary element of the group is actually called the opposite and denoted by minus x. There will be exceptions to this rule, but by default, these are the notations we use for abelian groups. To conclude our discussion on groups, I want to introduce the notion of a morphism. When you discuss algebraic structures, you don't just discuss objects like, say, groups, but also maps between those objects that are in some sense compatible with the underlying algebraic structure. Let's see an example here. A group morphism from a group G to a group H is a function in particular from G to H, which intertwines the operation on G and the operation on H. Formally, let's call the operation on G star and the operation on H box time. Then pi is a morphism if it's a function from G to H such that for all G and G prime in the group G, if you apply pi to G star G prime, you get the same result as if you apply box time to pi of G and pi of G prime, in that order. So you can see that the map sort of agrees with the operations in the sense that if you do an operation in G and then apply pi, or if you apply pi first and then do the operation in H, you get the same answer. In general, if my groups are not abelian, it's important that we keep the orders the same between the elements. As a simple exercise, you can check that the composition of morphisms is a morphism, and the identity of any group is a morphism for that group. For a mathematician, what this means is that groups and their morphisms form what we call a category. I like to think of it as a little universe in which you are doing mathematics about this particular structure, groups and their associated maps. Now, this was our discussion of the first algebraic structure we talk about in this class, groups. And the reason I remind you why we introduce them is because a set of vectors of the plane or in 3D space is an abelian group for the addition of vector. The addition of vectors has all the necessary properties. However, there is another operation on vectors, a scalar multiplication or scaling operation. And to capture the properties of the scaling operation, I'm going to need to introduce the notion of a field, which is a generalization of the algebraic structure of the real numbers. So here's our definition. A field is a set with two binary operations. One is an addition, and one is a multiplication, with the property that your field with the addition is an abelian group. As an abelian group, it has a neutral element called 0. And if you remove 0 from the set underlying your field, then that with a multiplication becomes an abelian group as well. In addition, there is a connection between the addition and multiplication beside the one already listed here, and that is distributivity. For all x, y, and z in your field, x times y plus z is x times y plus x times z. So this is a field. It has two operations, and they're related by distributivity, and they give you groups. Examples abound. The field R of real numbers is an example of a field. The field C of complex numbers is another example of a field. The field Q of fractions of integers is yet another example of a field, but the integers themselves do not form a field, because once you remove 0 for the integers, what you are left with does not form a group for the multiplication, as for instance 2 does not have an inverse as an integer. Groups can be finite. The quotient of z by pz, where p is prime, actually is an example of a field. Sorry, not a group, a field. Of course, group can also be finite. So the smallest field in particular is a field 0, 1. That's the smallest possible field because once you remove the neutral element for addition, namely 0, you are left with 1, which is a neutral element for the multiplication. By our definition, we must have 1. So this is the smallest possible field. I will adopt a few conventions in these lectures. When an operation is denoted by dots, it is a convention in mathematics that whenever it does not create any confusion, we simply don't write it at all. So x dot y will very often be simply written as xy. Second convention is that in a field, I have actually the abelian group for the addition. The field itself is, in particular, an abelian group for its addition. And so, as usual, we denote the neutral element by 0. But I also have the neutral element of the abelian group obtained by taking k and removing 0 from it. This is an abelian group for the multiplication. We can't call that neutral element 0, so we give it a different name. We call it the unit, and we denote it by 1. Now, let's prove a couple of simple properties about the algebra taking place inside of a field. This is going to be a theorem we're going to prove in the same vein with the same sort of philosophy as we did our proofs for theorems about groups so far. And it's the same sort of idea. It's a theorem that tells us that various basic algebraic properties we wish to be true in a field indeed are, but we did not need to assume them. They follow from the assumptions of what a field ought to be. I'm going to prove each assertion one at a time. The first assertion is that distributivity also works on the right. Well, this of course follows from the fact that multiplication is commutative and that there is distributivity on the left by assumption. So if you calculate x plus y times z for x, y, and z in your field k here, then first thing is you can use commutativity of the multiplication. This is equal to z times x plus y. Now you can use left distributivity, which we assumed in the definition of a field. So this is zx plus zy. And then again, we use the commutativity of the multiplication to rewrite this as xz plus yz. And you see we get the identity we desired. So we can expand on the left or on the right in a field. Second of all, I'm going to prove this important result that the product of two elements of the field is 0 if and only if at least one of the factors is 0. First, let me prove that 0 times anything is indeed 0. So I pick an element in my field, and I'm going to start computing a strange quantity a priori, probably, 0 times x plus 0. Well, 0 being neutral for the addition, this is certainly equal to 0 times x. Again, because 0 is neutral for the addition, this is indeed equal to 0 plus 0 times x, because 0 equals 0 plus 0. Using distributivity now, this is in turn equal to 0 times x plus 0 times x. Now, let's look at the beginning and the end of this equality. Because k with the addition is a group, we proved, this was the very first proof of these lectures, that 0 times x plus 0 equals 0 times x plus 0 times x implies that 0 times x must be 0. We can, quote unquote, cancel 0 times x on both sides of the equality. So we have proven that 0 times anything in the group, in the field, is equal to 0. Now, because my field in particular is commutative, it's a commutative object, that is, the addition is commutative, so is the multiplication, but here the addition is commutative, we suddenly get that x times 0 is also equal to 0. Actually, I'm using the fact that the multiplication is commutative. Now, I'm going to make a little aside here before proving the converse to this, because if you pay attention to the definition of a field, I only assume that the multiplication is associative on K without the singleton 0. Because that's what I assume that's a group, so automatically the multiplication is associative. But I didn't say anything about what happens if you multiply 3 elements and one of them at least is 0. Is the multiplication actually associative on all of K? Well, let's prove that indeed it is. So if I take 3 elements in my field that are non-zero, then since I'm assuming that the set K without 0 together with the multiplication is a group, associativity applies. Next, suppose that, for instance, x is 0. And say y and z, I'm not saying anything about them, just x is 0. Then let's calculate first x times y times z. Well, since x is 0, I just proved to you that x times y is 0, because 0 times y is 0. So x times y times z is equal to 0 times z, and that in turn again is equal to 0. On the other hand, x times y times z, well, x is 0, so that's equal to 0 times y times z. And again, by the proof we did just a moment ago, this is equal to 0. So you see that, well, both quantities are equal and they're in fact equal to 0. The two other cases, that is when y is 0 or z is 0, are done in the same way. You can check for yourself. So indeed, the multiplication is actually associative on all of K. I'm going to use this to prove the second bullet point. We have already half of it. We've proven that if x is 0 or y is 0, then x times y equals 0. Now I want to prove the converse of that. So I give myself 2 elements of my field K, whose product is 0. X and y in K, so that x times y is 0. Assume for a moment that x is actually not 0. Since K without 0 with a multiplication is a group, there exists an inverse for x called x inverse. That is an element x inverse in K, so that x inverse times x is equal to 1. Then I'm going to make a little funny calculation again. 0 is equal to x inverse times 0, because 0 times anything is always 0. We proved that. But I can replace 0 by x times y, since by assumption x times y is indeed equal to 0. Then I can use associativity of the multiplication. I just proved that the multiplication is associative on all of K. So I move the parenthesis. But then I recognize that I have x inverse times x, which is equal to 1. And 1 times y is simply y. So if you look at this string of equality, I have indeed proven that 0 is equal to y. If x is not 0, y must be for the product to be 0. This actually proves completely the second bullet point here. There is an important corollary to this property we have just shown. And that is that if you take an element in your field, you can take its opposite for the addition. That's called minus x. That's the element which, when you add it to x, gives you 0. Or you could multiply x by minus 1, that is the opposite of 1. And those two, well, which is a good news, are indeed equal. But they're not a priori the same. The minus x comes from the structure of the field with the addition as a group. It has nothing to do with the multiplication at all, a priori. Whereas minus 1 times x, well, mostly involves the multiplication, but it involves the addition a tiny bit because we have to define minus 1 as the opposite of 1. But nonetheless, this relates the multiplication and the additive structure in a very interesting way. Let's check the proof. Let's take an arbitrary element x in your field K. So we know that, well, minus 1 times x plus x, we can calculate that because this is minus 1 times x plus 1 times x. That's a point of 1. 1 is a unit that is a neutral element for the multiplication. So x equals 1 times x. But then I can use distributivity. And I can factor x. And I get that this expression, minus 1 times x plus x, is now equal to the sum of 1 and minus 1 times x. But the sum of minus 1 and 1 is 0. That's by definition of what minus 1 means. So we end up with 0 times x, which we have proven has to be 0. Therefore, minus 1 times x plus x is 0. We have an abelian group here, so for free, we also get that x plus minus 1 times x is 0, so addition is commutative. And we have proven early in this lecture that the opposite of an element in a group is always unique. Therefore, minus 1 times x must indeed be minus x. That's kind of easy, but very, very fun and pleasant little proof, which also is a bit reassuring that we can do algebra a little bit like we are familiar. This last property is also the sort of little things we need to be careful about. It relates multiplication and opposite again. So I give you two elements of the field, and I can do a few calculations like this. I can take the opposite of, say, one of element and multiply it by the other. Or I could simply multiply my two elements and then take the opposite of the result, of the product. And as we see written here, there are three different ways we could do that, and luckily they are all equal, so there is no confusion. Well, let's try the calculation. So for instance, I'm going to take an x and a y and k, and I'm going to compute x times minus y. But by the work I just did, minus y can be replaced with minus 1 times y. So we are calculated now x times minus 1 times y. I can now use associativity of the multiplication. We prove that the multiplication of k is associative everywhere. So I move my parenthesis to the left. Then actually I have that the multiplication is also commutative. So I move the minus 1 all the way to the left. And then minus 1 times x, for the same reason as before, is minus x. Therefore, indeed, x times minus y is equal to minus x times y. Again, keep in mind, minus x and minus y are defined through the additive structure. But thanks to the work we have done, we see that we can still move the minus sign around because really we could transform the minus sign into a product with minus 1. We can do the same thing here to prove the other equality. So if you calculate minus x times y, another thing you can do is, well, as I said, you write minus x as minus 1 times x. We've done that a few times now. And again, you can use associativity. So this is equal to minus 1 times x times y. And that is indeed by the bullet point number 4 here, equal to the opposite of xy, the product xy. So we have proven our theorem entirely. And so we see that the algebra in a field at least has some similarities with the algebra you're familiar with the real numbers. Of course, not everything is quite that simple, but for our purpose, those properties will serve us well for the next few lectures. So in the next lecture, we now have all the necessary ingredients to define the notion of a vector space.